Now we're going to look at a box that's being pulled at an angle. We're going to use the coefficient of kinetic friction in this case. Now remember, whenever we talk about the coefficient of friction, the smaller the number, the more slippery the surface is, the less that it's opposing the force of motion. And that's what all that number is telling us. Now, kinetic friction is the friction that's occurring once a box is moving. The static friction, you remember, is the friction force that's occurring when it's sitting still. So here we have a box that's being pulled with a force of 156 newtons at an angle of 25 degrees to the horizontal. The box has a mass of 35 kilograms. The coefficient of kinetic friction between the box and the floor is 0.25. Remember, there are no units for this. Find the acceleration of the box. Oh dear, this sounds like a lot of work. So let's dig in and get going. We're going to begin by drawing a free body diagram. So let's draw a free body diagram of our box so that we kind of know what we're getting into here. We've got a box that has a mass of 35 kilograms. We know that it's being pulled at a force of 156 newtons, and that is at an angle of 25 degrees to the horizontal. Uh-oh, I can feel some trigonometry coming on. All right, so this is what we know, and we're going to save this coefficient of kinetic friction for later. We do know that one, but that's coming up later. Now they're asking us to find the acceleration of the box. Think about formulas that you know for acceleration. If you thought of F equals ma, you're on the right track. But this is the net force. So we need to know the net force on this box. We already know the mass. And once we know the net force, then we can find the acceleration. So let's work our way around and find the net force, which is the total of all the forces on this box. I'm going to start with gravity first. This is the force of the weight of the box in the downward direction. We find this by multiplying the mass times little g, or 9.81. So this is going to be 35 times 9.81 meters per second squared. All right, so 35 times 9.81, 343. Let's just use that. So the weight in the downward direction is 343. Now you remember when we looked at one of these previously that our box was sitting on a horizontal surface, and so we just used the same force for the normal force in the upward direction. But that's when we had an applied force that was horizontal. Here we have one that's at an angle. So we can't use the number for the weight because some of the normal force is being taken out by the vertical component of our applied force. So we have to find this vertical component of our applied force in order to find the normal force. We're going to use, I should have put a y there. We're going to use the horizontal component to find our applied force. It's the only part of it that's actually doing any work in the horizontal direction. All right, so let's go ahead and find that. Now, y, you'll notice, is opposite our angle 25, and we use sine of theta is equal to opposite over hypotenuse. My 156 is the hypotenuse. My theta is 25. I can multiply my hypotenuse by both sides and find my opposite side, which is what I'm looking for. So my opposite side, which is going to be that vertical component of my force, is going to be equal to the sine of 25 times 156. Let's put that in. Remember to make sure that your calculator is set to degrees. So I'm going to make sure, oh, it is not set to degrees, it is set to radians. There's set it to degrees. All right, so I'm going to do sine of 25 times 156. It's close enough to 66 that I'm going to call that 66. So this opposite side is 66. And that's newtons, 66 newtons. So part of my normal force is taken up with this 66 newtons. So I'm going to do 343, which is what it would be in the upward direction if I didn't have that, minus 66. So this normal force is 343 minus 66. So what is that? 343 minus 66, 277. So my normal force is 277. All right, now let's find our applied force in this direction. Okay, my applied force is going to be, well, it's the adjacent side now, so I'm going to use cosine. So that x side is going to be equal to, my adjacent side is going to be equal to my cosine of 25 times 156. So cosine 25 times 156. 141.38, we'll just call that 141. All right, oops, I don't want to close that. Okay, 141 newtons. All right, so now I've found 3 of my forces, but remember, I've also got friction going on back here. Now my coefficient of static friction comes into play. Okay, my coefficient of static friction is 0.25. And I want to know what the force of this friction is. And that's going to be equal to the coefficient of kinetic friction times the normal force. Right, so we're going to do 0.25 times 277. All right, 69 newtons in this direction. So that means I really don't have 141 newtons of my applied force that's actually pulling the box. What I really have is 141 minus 69, and that's going to give me my net force. Now let me explain that again, because when we talk about net force, we're talking about taking into account all the different forces. The force of weight is in equilibrium with the normal force that is including the vertical component of our applied force. The horizontal force, the 141 newtons, is being counteracted by the 69, so we have to subtract, and we find our net force by doing 149 minus 69. So 141 minus 69 is 72. Okay, so 72 is our net force. Just write this right here and put like a little box around it because we're really not done. Oh dear, what did I say that was? 72. Yeah, senior moment. Okay, so 72 newtons is our net force. But they don't want net force. They want to know acceleration. Well, at this point, it's a piece of cake because we know that our net force, if we go up here to the top, the net force is equal to mass times acceleration. Okay, so force equals mass times acceleration, but we're looking for acceleration, so we'll divide both sides by mass. So acceleration is equal to force divided by mass. 72 divided by 35, which is the mass of our box. And we get 72 divided by 35, 2 meters per Problem solved.